So we're solving some MCQ on chapter 11. The first question, a wheel rolls without slipping along a horizontal road as shown. The velocity of the center of the wheel is represented by the arrow here. Point P is painted on the rim of the wheel. The instantaneous velocity of point P is, so this point P right here at the bottom of the wheel, we talked a little bit before on this in our study of rolling motion. What we notice in rolling motion is that different points of the object will have different speeds. Namely, we were combining the translational motion of the center of mass with the rotational motion of the object around an axis. So there's pure rotation with pure translation, and we combined both to study rolling, right? If I study the center of mass alone, this center of mass is undergoing translation or rotation motion. So the center of mass or the center of the wheel is over here, right? At the middle. This center is gonna feel translation or rotation. It will feel translational motion. How do we tell? One, it is on the axis of rotation itself. So it's not really big, it's not gonna be undergoing any rotational motion. And it is gonna be undergoing a translational motion. Namely, when I study the translational part, I represent the wheel, all of it, by a point at the center of mass, and I study this point. So the center of mass alone is just undergoing translational motion. On the other hand, the points at the rim and at the edges and in between, they are going to be feeling some rotation, and they can be undergoing some translation as well, right? The point at the top, namely, is feeling a motion that is to the right, let's say, a speed that is to the right, and it's undergoing some angular speed as well. The point at the top, if you check its speed, it will be double the speed at the center of mass, whereas the point at the bottom has zero speed. This is actually represented in the first slide of this chapter. So I'll open it just for you to see. Here it is. So you can see how the point at the center has a speed equal to the speed of the center of mass. The point at the top has a combination of both rolling and rotation and translation during the rolling motion. It will have double the speed of the center of mass. How do we tell that? We actually equate the angular velocity everywhere and solve for the linear velocity. The point at the bottom is actually a point where the wheel is always momentarily at rest. This point at the bottom is momentarily at rest. Why? The force it feels is just the friction, by the way. The friction force will not cause any motion for the wheel. Rather, it's just gonna tilt the wheel to undergo some rotation. This wheel in particular, if there was no friction at all, what will happen to it? It will just move linearly due to the, I don't know, engine force maybe. It would just move without any rotation if there was no friction. Because the only force that is causing the rotation here is the frictional force. So the friction is causing rotation, but not translation. The result is that it tilts the direction of the wheel motion without just moving the wheel all of it together. So if I go back to my MCQ, this is just a conceptual question. Point P here will have zero speed. The center of mass, by the way, so point P here, zero speed. If I ask you about the center of mass, what is the direction of the speed at the center of mass? Is it also zero? It's to the right, correct. Here it is. What about this point? Let's name it Q. This is double the speed of the center of mass, all right? In order to have a resulting rolling motion. So this is 2 VCOM, this is VCOM, and this is 0. We're asked about point P, this is 0 speed. Let's take a look at this question. This is a nice one. A wheel of radius 0.5 meters rolls without sliding on a horizontal surface as shown, starting from rest. Let me just share the right file. Hmm. Did you solve them in the recitation? Did you solve these as well? So I basically put several problems. Who hasn't taken this in the recitation? Okay. Did you solve these, Amir, in the recitation? This problem? Okay. Yeah, it's easy. It's easy. Okay, I'll solve these quickly and then I'll move on to the other ones. So I'm interested here in the distance traveled by the center of the wheel from t equals 0 to t equals 3 seconds. The wheel has a radius 0.5. It is rolling without sliding. When I say without sliding, this means I have a pure rolling motion in which the center of mass has a speed which is translational only. The edges, I can take a pure rotation and combine it with the translational motion of the center of mass. So I will always put the condition of no sliding or no slipping. Starting from rest, the wheel moves with constant angular acceleration, 6 radian per second squared. So be careful, this is alpha. The distance that is traveled by the center of the wheel, that's what I'm interested in. So this is basically the center of the wheel. This is the center of mass. So what I want is the distance covered by the center of mass. I know the center of mass undergoes no rotation. So I'll just apply translational motion to the center of mass. I'll take the distance covered by the center of mass to be none other but half at squared plus v0t. This is basically the distance covered because the center of mass undergoes only translational motion. Okay, let's see what we have. It starts from rest. So this is gonna go. Alpha is equal to A over R. Excellent. So A is going to be alpha times R. This is 6 times the radius, which is also given. So I got 3 here. So I'll just plug 3 times, and the time is 3 seconds. So this is going to be 13.5 meters, answer B. Two wheels roll side by side without sliding at the same speed. V1 equals V2, speed, not angular speed. The radius of wheel 2 is twice the radius of wheel 1. So I'm telling you, wheel 2 has twice the radius of wheel 1. The angular velocity of wheel 2 is, so I want to compare W2 versus W1. So what I'm going to do is, I'll use the formula. Is it going to be the same angular velocity? How do we tell? I know omega is V over R, right? So V2 over R2 equals, is it going to be equal to V1 over R1? I know they have the same translational speed. So I can write R1 omega 1 equals R2 omega 2, right? This is definitely correct. Now, I know that the radius here is twice the radius R1. So I have R1 omega 1 equals 2 R1 omega 2. I end up seeing that W1 is 2 W2, right? So the angular velocity of wheel 2 is going to be half that of wheel 1. This is answer C. Questions? A thin-walled hollow tube rolls without sliding along the floor. The ratio of its translational kinetic energy to its rotational kinetic energy is, so I have K translation equals, I want K translational over K rotational. That's what I want, right? Okay. How do I proceed? I'm gonna write down the formulas. Half mv squared over half I omega squared. Very nice. Half and half go away. I will have mv squared over. This is a thin-walled hollow tube. So I'm gonna go to my table of rotational inertia. Yes, the table as it is given in the exam, yes. Here it is. So I want a thin hollow tube. This is basically the same as the hoop, right? Because it's thin, so it's not going to be having an inner and outer radius. So I'm going to take the hoop. This is I equals mr squared. So I'll have here mr squared, and omega is equal also to v over r, right? So I'll have v squared over r squared. Let's look at that. It cancels out to 1. So the ratio is 1. A forward force acting on the axle accelerates a rolling wheel on a horizontal surface. If the wheel does not slide, the frictional force of the surface on the wheel is, so definitely there's some friction, right? What is the direction of this friction? I have a wheel, it's connected to the axle here, and I pushed the axle, so the wheel should be pushed forwards, right? If there was no friction, the wheel would move without rotation, right? We said the friction is the reason behind the rotational motion because it's actually the only force that makes a non-zero torque. So if there was no friction, the whole wheel will just move forward without rotation. So the friction is always opposing the direction of motion or the direction of possible motion. If the motion is forward, then the friction should be in which direction? Backwards. So here the friction is backwards. If I look at the options D and E contain backward direction, what's the difference between the two? The friction does zero work on the wheel or it does positive work on the wheel. So like we said before, the friction contributes to the rotational motion. It doesn't contribute to the translational motion of the wheel. So it will actually do no work, namely because the friction is applied at the bottom of the wheel. Do you all agree? And this point is momentarily at rest, always. So point P is always a point where the speed will be momentarily zero. So there's basically no displacement, and then there is no work done. So there will be no work done. This is answer D. A solid wheel with mass m, radius r, and rotational inertia mr squared over 2 rolls without sliding on a horizontal surface. A horizontal force F is applied to the axle, and the center of mass has an acceleration A. The magnitudes of the applied force F and the frictional force of the surfaces, respectively, are. So we want to study the forces and the frictional force. I have a solid wheel, its radius is r, its rotational inertia is given. I'm just going to apply Newton's laws for translation and rotational motion. So if we study F net equals ma, I have two forces, the frictional force and the applied force. So I'll have F minus F equals ma. For the torque, only the friction will contribute to the torque. We talked about this quite a lot before. I is half mr squared and alpha is a over r. We end up seeing that F is half ma, which is one of these three options. What about capital F? So capital F will be F plus ma, which is going to be 3 over 2 capital M A. So this is basically answer E. The coefficient of static friction between a certain cylinder and a horizontal floor is 0.4. The rotational inertia is half mr squared. What's the maximum acceleration the cylinder can have without sliding? So I just want to study the acceleration. I know I have the static friction is 0.4. Notice how we were always using the maximum static friction in our formula for rolling motion. We always took static friction, although the object is moving. Why? Exactly. Our point P at the bottom is a static point, so I'll use static friction. This is a point which is always momentarily at rest, so the friction that will be applied will always be a static friction. I want the maximum acceleration, so I'll take the maximum friction and solve for the maximum acceleration. I can either use this or F net equals ma, which one is always preferable in this case? I'm studying friction, which does it make a torque? Yes. Does it make a translational motion? Sort of. It cancels part of the applied force, so it will show up in both equations. But I prefer to take the rotational equation. Why? So I'm really gonna use tau equals I alpha. I will not use Fnet equals MA, because in Fnet equals MA, in addition to the friction, there is what? The applied force. There's also the applied force, which I don't really know anything about in this problem. If I solve the rotational part, the applied force doesn't show up. So I can just have the friction as my only unknown, and I can solve for the acceleration. Namely, you can see I'll have F equals half ma. Now the friction, what we want is the acceleration, right? I can see that A is going to be 2F over m. How do I proceed? Exactly. I'll use the formula of friction, mu(n), and the normal is equal to, sorry, this is a mass. The normal is equal to mg here because it's a horizontal floor. Can you see? Yeah. And I'll have the mass here again. This cancels out. I end up with 2 ug. And mu is 0.4, and I end up with 0.8 g. Very nice. Very interesting, right? There was one more question I wanted you to take a look at. This is chapter 9, really. I just found it interesting to just mix. So I want to find the speed of the center of mass of the below system. Our system contains, what does it contain? 2 points, 2 masses, and here we can study the center of mass itself, but here I'm interested in the speed of the center of mass. To find the speed of the center of mass, we have a formula very similar to the position of the center of mass, right? We solved before x center of mass is x1 m1 plus x2 m2 over m total, right? A similar formula is there for the speed of the center of mass. Namely, I'll take Vx alone and Vy alone, and I'll put Vx1, m1 plus Vx2, m2 over m total. And here I'll have Vy1, m1 plus Vy2, m2 over m total, right? So I'm just gonna apply. I have here, I'm gonna check the speeds that I'm given, right? What am I given for the speeds? Let's name this particle 1, and this is particle 2. What's the speed of particle 1, by the way? Particle 1 has this speed, which is to the left, right? So I'll write this V1 is minus 2I plus 0j. I use this so that I can see clearly the x and y components and plug them in. V2 is equal to 0I plus 3j. Makes sense? And the rest is really just some plugging. I'll have here minus 2 times 6 kilograms plus 0, over the total mass, which is 9. And here I'm going to have 0 plus 3 times 3 over 9. Correct? So I'll end up with minus 12 over 9. And here I'll have 9 over 9, which is 1. So I was able to find the speed of the center of mass. Do I stop here? Yeah, I should find the magnitude. So I'm going to say V of the center of mass is radical Vx squared plus Vy squared. This is radical 1.33 squared plus 1 squared. I can solve for this. I got 1.67 meters per second. So this is, I found the speed. as it is, as a magnitude, right? I could also ask you to find the direction, then you apply tangent theta, which is Vy over Vx, and you find theta, right? Any questions? Okay, let's check these two problems on rolling motion, which are also nice. So here I'm really combining the situation which we have seen in chapter 8, where I had gravitational potential energy, and we were just studying any object as a single point, and I would equate energies and study that this point is moving down. Same situation, but now I'm accounting a little bit for the rolling motion. And in that case, the sphere is no longer acting as a point, and I will check rotational energy that is also involved. So let's read the question. I have a solid brass ball of mass 0.28 grams. It will roll smoothly along a loop-the-loop track when released from rest along the straight section. The circular loop has a radius 14 centimeters. So this loop has a radius 13 centimeters. The mass of the brass ball is 0.28. Yeah, you're right, it's 14. Thank you. Okay. The ball has a radius r, which is less than this radius. What is h if the ball is on the verge of leaving the track when it reaches the top of the loop? So I want to find the height here such that when the ball reaches the top of the loop, it's on the verge of leaving the track. So it's almost losing contact. So I have two special cases when I study the top of any loop. Which is either I tell you it's momentarily at rest, this means the speed at the top is 0, or I tell you loses contact, this means what? The normal is 0. We have studied this in chapter 6, and I could have no special case, some regular speed, some whatever case, you know, it doesn't have to be either one of these two. So here I told you it's almost losing contact. So I know that the normal is 0. When I see that the normal is 0, I will study forces. So شوفوا what I did. I said it's almost losing contact. The normal is 0 at the top point. At other points, it's not 0, definitely. And so I will have F net is going to be just the weight force at this top point. What are the forces we're going to have? Just the weight force. There is no normal force. The weight is downwards, and I can study the centripetal direction. I know in the centripetal direction, the acceleration is going to be equal to v squared over r. So here F net equals mv squared over r, and F net is mg, so I'll have mg equals mv squared over r. Now, one important remark, notice what I substituted for the radius. For the radius here, I put r minus the radius of the small sphere. Why? So this is my sphere. It was over here. It came over here. It is ascending. It reaches the maximum point. What's going in a circular motion for the sphere is the center of mass. So what I will apply, Newton's second law here for, is the center of mass. And this center of mass is moving through which circle? Not this big one with radius r, but this slightly smaller path, which has a radius r minus a small r, which is the radius. So I have to like just subtract this radius r of the sphere itself. Yes. Yeah. In this case, actually, it doesn't make a lot of difference. You're right. But I wanted to put the general case for you. It might be useful. Yeah. Okay. So I started with the general case, and then I can definitely approximate r minus r to be just equal to r in this particular case. Other questions? Okay, so what can I find from this equation, really? I found the speed, right? I can rearrange for the speed, but what is the question? I want the initial height so that we reach this point with the normal being equal to 0. I just got my first condition for the normal to be 0, the speed has to be this much at the top. All right, I'm gonna use this and plug it in some equation that will give me height. Whenever you have speed and you want height, always think what? Huh? No, I have speed, I want height. Always think mechanical energy, gravitational potential energy, right? When do we have a speed and we find a maximum height out of it, or we have a height and we find the speed out of it? It's when we apply conservation of energy, right? I would think kinematics if I have speed and I want distance, not height, right? Yeah. So I'm gonna apply energy conservation here. Now, the energy conservation equation is going to be a bit interesting. It's a bit twisted from the translational motion, namely because the ball is rolling, then in addition to the translational part, yeah, Amir finds this very fascinating and interesting, and he's a bit concerned now. So we're going to add just the energy that the ball will carry due to its rotational part, all right? So all I did was, for the mechanical energy, I put the kinetic energy to be a translation plus a rotational kinetic energy. So in fact, an object that is moving linearly has less energy than an object that is moving both with a linear and rotational motion. And that makes sense, right? The rotational part has some additional energy carried by the object. So I inserted the initial energy and equated it to the energy at the top. Now, the initial point, it's the point over here. The ball was released from rest, so there is no kinetic part. I'll just put 0 for the kinetic energy, both rotation and translation, and I will have a gravitational potential energy, right? Which is mgh. What do I want to solve for? I remind you, what are we trying to find? H. And here it is. It's showing up in an equation. That's perfect. Yes. Good point. If there was no friction, then we have slipping, yes. And then I have only translational motion, absolutely. But then it will not be rolling, you know? You will not be told that it's rolling from the first place. If I told you it's rolling, definitely there is some friction here. Let me just close the tab here. Okay. All right. So at the point which is at the top, I'm gonna have some non-zero kinetic energy, right? So I'll put the translational kinetic energy, half mv squared. Vt is the speed at the top, which I just found here, right? Here it is. So I'm gonna plug this right here. For the rotational kinetic energy, I have half I omega squared. What's cool is I can always revert back and relate this to the translational quantities. So I will substitute omega by v at the top over r. So the speed at the top is other but this speed, which I found before. I'll plug it here. And I is that of the case that we have, which is what? I have a solid brass ball. I go back to my table of rotational inertia, and I have two cases for spheres, a solid sphere and a thin spherical shell. Our case is a solid sphere, right? So it's like one that is empty inside and one that is filled up with the material inside. Our case, we are told it's a solid sphere, it's not empty inside. This would apply for a basketball, for example, this case, all right? So in our case, we have this case, and how much is the rotational inertia? It is 2 over 5 mr squared, all right? So I'll plug this in. Any questions? So I'll just substitute this here. 2 over 5 mr squared. And we still have a gravitational potential energy at the top. Namely, at the top, the gravitational potential energy is equal to mgh, where h is the height over here, which I substituted as 2r. You can put it as 2r minus too small r, right? But r is way smaller. It's not going to have a big effect. So yeah. So I did some simplifications here. Remember, E initial had only a gravitational potential energy part, and E at the top point has translational kinetic energy, rotational kinetic energy, and gravitational potential energy, right? I canceled M everywhere, and then I canceled G everywhere. Just a second. Yeah, so I substituted VT, which was in terms of G, right? I used VT, which is radical G into R minus R. So I substituted that here and I solved. Notice how at the end I removed small r, right? You can from the beginning, because I told you R is way smaller than capital R, you can cancel it out, but I prefer to put the general case for you to see it, all right? Okay. And I'm given the radius of the circular path, so I'll just plug this here and I can find the height. Now, I wanted to see part B. So the ball is now released from h equals 6r. Okay, how much was h in part A? We solved for it and we found that it was 2.7r, right? Now I started from a larger height, right? What will be the result? Definitely the speed at the top is higher and our ball will not be really at the verge of losing contact. So I will not put the normal to be equal to 0. And anyway, in this part, they ask us about the point Q, which is over here at the side of the circular path. What do we want to know about point Q? So I gave you the initial height is 6r. I want the magnitude and direction of the horizontal force component acting on the ball at point Q. The horizontal force component. All right, let's take a look at the forces I have at point Q. Namely, at the point which was at the top, because I lost contact, I did not put a normal force, and the only remaining force was the weight, right? At point Q, I still have that weight, but I will add to it which force? The normal. It's not 0 here. The ball is not at the verge of losing contact. And the normal is a normal. When I say normal is a normal, I mean the normal is perpendicular to the path, right? By definition, the normal force is always perpendicular to the surface. Where is my surface? I'm interested in this point here at the edge. So this is my surface. The normal is normal. So it's going to be perpendicular. So it's going to be in this direction. It's not to the right, definitely, because the normal is exerted by the surface to support the objects. So the surface is here, the object is here, the surface will support it by applying a force towards it to push it from basically like passing through, right? So the normal is over here. So I'll just redraw my figure. This point here has these forces, weight and normal. What is the question? I want the magnitude and direction of the horizontal force component acting on the ball at point Q, which is none other but what? Yeah, I want the horizontal force component. The weight has no horizontal component. So what we want is the normal force itself. How do I solve for the normal force itself? I'm going to apply the centripetal direction. I will apply Newton's second law along the centripetal direction, right? And in the centripetal direction here, I'll say F centripetal equals mv squared over r. V is the speed at point Q, and F centripetal is the normal itself. Do you agree? Okay, I want the normal, right? I have the mass, I have the radius of the circular path. What's missing? Yeah, I need the velocity. How do I find this velocity at point Q? So I'm studying point Q over here. I have a weight force here. I have a normal force here. And we have started from this point, which I gave you its height is 6r, right? We deduced that the centripetal component of the force is mv squared over r. And this centripetal force is the normal itself at point Q. we need V at Q to find the normal, right? How do we find the speed at point Q? Given a height, finding speed, as usual, I'll study conservation of energy. Excellent. So I'm gonna take conservation of energy. So here it is. I'm gonna solve it with you here. So I'll put, as usual, E initial, which is just a gravitational potential energy, right? mgh initial, which is mg6r, equals E at which point? I'm not interested in the point at the top now. Which point am I interested in? Q, the point that is at the right, this point, because I need the speed at this point to deduce the horizontal force at this point, which is the normal force, right? Okay, so I'm gonna put here E at Q, and the mechanical energy at Q is half mvq squared plus half I omega q squared plus mgh at Q. The height at Q is just, how much is the height at Q? Yeah, I'm taking this point to be the 0 level. So the height here to the top is 2r, this is the diameter, and the height of Q is the radius itself. So this point Q over here has this height, which is this height, which is the radius itself. So I'll just put mgr. And here I'll have half times 2 over 5 mr squared into v squared at Q over r squared. And here I have half mvq squared, right? What do I want from this equation? What am I trying to find? Yeah, I need the speed to plug it here and find the normal. So let's take a look at what we have. I'll separate the speed alone and the other components alone. I'll have mg6r minus mgr equals, so I brought this over here, half m vq squared, this term I dropped it as it is, plus this term I'll drop it here, but first I'll cancel r squared and r squared, right? And 2 and 2. Makes sense? 1 over 5 m vq squared. Makes sense? Okay, I'll just rearrange. Notice how the masses cancel out. And 1 over 2 plus 1 over 5 is basically 5 plus 2, 7 over 10 vq squared. And this is 5 gr. Correct? Perfect. So vq is going to be equal to 50 over 7 gr with a radical, right? I will not really need to apply the radical because I have v squared here as well in the normal equation. So I'll have m dot v squared is 50 over 7 gr over r, 50 over 7 mg. Makes sense? Do we have the math? (0.28 grams). That's so tiny. I'll multiply times 10 power minus 3 to make this in kilograms, and then multiply by 9.8. Makes sense? We want also the direction of this force. It is to the left, right? Yeah. All you have to know is whether it's to the right or to the left. Okay.